Hello students, welcome back. We just completed part A of example 4.2. That was the left-hand side shading problem. All you had to do was to look up this z-table and then get the CDF value directly. Well, of course, that's not all you have to do, but that was what you had to do in the end. Now let's discuss the right-hand side shading. How do I know? Because the problem says x is greater than 17.03. So greater than, that means right-hand side. So please expect right-hand side shading. All right, let's begin. How do I do this? First, let's draw a picture. Outline, and then center, and that's of course 16.75. And then where is 17.03? It's bigger than 16.75, so it's in the right-hand side. Right here. That's 17.03. And then x is greater than 17.03, so this is the right-hand side shading. I hope you guys remember about right-hand side shading problem from section 3. If you look up the z-table in the end, you always get the probability toward the left-hand side shading. Here I want right-hand side shading, so we have to subtract from 1. Okay, remember that, and let's go over to z computation. Z is end minus center over SD, so 17.03 minus 16.75 over 0.451. X minus mu over sigma, or end minus center over SD. Either way, if you do this computation, I'm pretty sure you're going to get 0.62 approximately speaking. The same number we discussed in section 3. That was the design, by the way. So, if you go over to your standard normal table, look it up, look up 0.62, then you're going to get the probability for the left-hand side shading. Was it 0.7424 or something? I don't remember precisely what this number was. But in any case, this part is 1 minus of that. Because total area is always 1, and z-table gives you only the left-hand side. We want right-hand side, so we need 1 minus of that. Okay, that was the main idea. And let me get out of this drawing mode so that I can show you the real solution. All right. Okay, here we go. We need the right-hand side shading. Centered at 16.75, 17.03 is here. I want the right-hand side shading because x is greater than that. And then if you do your z computation, x minus mu over sigma, or end minus center over SD, you get 0.62. Now, if you look up 0.62 from your normal table, you're going to get, let's see, 0.62, 0.6, and then 2, you get 0.7324. Not 0.7424, 7324. All right, 0.7324, and do 1 minus of that. In the end, you get 0.2676. And that is the probability that we estimated. By the way, we ended up with the same result as in this problem here. Of course, that was by design. So if you have right-hand side shading, subtract from 1 because the normal table gives you only the shading to the left-hand side. Now, what if you want shading in between? You're going to find out both and then subtract one from the other. Remember, in part A, we did the z-score for 16.01, and part B, we did it for 17.03. Set up and subtract. I'm going to leave the details to students. By the way, here's a summary. Step 1 is to draw a normal picture. And here's my suggestion. Outline, center, end, and finally shade. That's what we need. Outline, normal picture. It doesn't have to be really pretty, reasonably accurate, and that's going to be sufficient. Center, again, the same deal. End, well, one is left-hand side and one is right-hand side. That kind of thing is important. If you have both of them in right-hand side or something like that, that's wrong. But the scaling, you cannot draw it accurately. So anything reasonable will do. But in any case, in this case, we have this kind of end, and thus we have this kind of shading. So how do we do that? Shade it all the way to the left from x2, and then shade it all the way to the left from x1, subtract one from the other. That's going to be the middle area. Basically, it's a geometry problem way back from high school or maybe in middle school. How do you get the z-score? End minus center over SD. Here we have two ends because x1 and x2, and they'll give you two z-scores. So you'll have to look up two probability values from the z-table, and then you'll have to do appropriate computation with those. In this case, appropriate subtraction. I'm going to leave the details to students. And that summary applies to any kind of forward problems, any kind of probability computation problem. All right, now, do we have enough time for inverse computation problems? Well, okay, all right. Similar situation, mu is 16.75, sigma is 0.451, and then how about this? Find out the first quartile, that is, draw a normal picture, and then centered at 16.75, and then over here, I'm going to find out appropriate x value so that this probability is a quarter, 0.25. How do we work it out? Well, do you recall what we did in section 3? We went to the standard normal table and got the closest z-score and did appropriate estimation. Remember? And that z-score is end minus center. So this x value you have to find out minus center, 16.75 over SD, 0.451, and that has to be appropriate z-score that you have to get from the z-table. You have to do some estimation. Now, once you have this z-value, all you have is just a linear equation. Solve it, and you're going to get the x value. How? Well, I'll have to get out of this drawing mode, so okay, pay attention to that. All right, let me get out. Okay, look up the z-table, and then 0.25 must be somewhere around here. Yeah, right here. 0.2514 and 0.2483, and that's pretty close to negative 0.67 or 68. So negative 0.675, approximately speaking. And that z-score is n minus center over SD. So basically what we have here is n minus center, 16.75 over SD, 0.451, is approximately equal to negative 0.675, approximately speaking. And from here, you can solve this equation. How do you solve this equation? Well, you can remove this denominator to the other side. X minus 16.75 is approximately equal to negative of 0.675 times this one, 0.451. And then if you flip this one to the other side as well, then you're going to get x is approximately equal to 16.75 minus 0.675 times 0.451, and then punch your calculator, you're going to get something. And that's exactly this equation. And in the end, what do you get? We have 16.44 something, 16.4458 approximately speaking. And the reason I put question mark here is because here I used how many decimals? Oh, no, I used too many decimal digits here. So this answer must be something a little bit more accurate than whatever you're going to get from this computation. So if you run Mathematica, you're going to get 4456 is what you're going to get if you use just 4 decimal digits. And if you use more decimal digits with Mathematica, you're going to get something a little bit more accurate, 16.4458. In any case, they're close enough. Very close, as a matter of fact. And that's the 25th percentile, or the first quartile. Now, how do you do something like this? So x is greater than something is 0.325. So in this case, it's basically you're doing this. If you flip it over to the other side, it's 1 minus of that, so 0.675. So this problem here is equivalent to this. So 0.325, right-hand side shading is 0.325. Therefore, the left-hand side shading is 1 minus of that, 0.675. So basically, you're doing this problem. So look up the z-table and then get appropriate z-score closest to this probability, 0.675. I hope you guys remember because we did it in section 3. And then you set up an equation, z equals to n minus center over SD. So the z-score is n minus center over SD, and that's approximately equal to some number you got. And then solve this equation, you can find out x value. If you do it right, you're going to get about this number. I'm going to leave the details to the students.